Welcome to Lecture 16, 4.2, Least Squares Regression. Alright, so once the scatter diagram in a linear correlation coefficient shows that two variables have a linear relation, we can find a linear equation that describes this relation. One way to do this is to select 2 points from the data that appear to provide a good fit. Okay, so this space should not be there, it should be over there. Hopefully I fixed that in your notes. Alright, the line drawn appears to describe the relation between two variables well, and to find the equation of the line through these 2 points. Alright, so a quick review on lines. This is something done normally in Algebra 1 or Algebra 2, or maybe college algebra if you took it in the college level. So given that m is the slope of your line, and that x sub 1, y sub 1, and x sub 2, y sub 2 are points, and that b is your y-intercept, we have the following. So, point-slope form for a line. That is y minus y sub 1 equals m times x minus x sub 1. This is called point-slope. Easy way to remember this? These are the, let me change my pen. These are the items that you would be filling into this equation. Your 1 point in the green, and your slope in the blue. If you read this from left to right, which is how we read things, the first item you notice is your point, and then the next item you notice that you input is your slope. Hence the name point-slope. Alright, the next slope, or the next equation for line is called slope-intercept. Y equals mx plus b. And what things do we input here? Well, we input the slope, and then we input this guy here, b, which remember is the y-intercept. So if I read this from left to right, this is slope, intercept. Hence the name slope-intercept form. So oftentimes, to create the equation of a line, unless you have your exact y-intercept, which is kind of hard to have, it's easier to start with this form and work your way to this form, because oftentimes people want the final answer to be in your slope-intercept form. Now let's take a look at some of the formulas for slope. So remember, slope is the way, or slope is describing the way your line is sort of tilted on a graph. So maybe it goes down, or maybe it goes up, and so on. So some of the equations. One of the simplest ways of finding slope is by just looking at a graph and counting rise over run. How quickly you would get from one point to the next. Now this is easy if you're actually given a graph. Another way to find it is m equals y sub 1 minus y sub 2 all over x sub 1 minus x sub 2. We use this when we're given 2 points, like above here. The last way that is known for finding slope is we use this formula right over here. Y equals mx plus b. So if you're given an equation, you just rewrite it in slope-intercept form, and whatever is near your x is your slope. Notice we don't include x in the slope. It's just the number near x. Okay, so that was a quick review there on equations of lines. Let's go ahead with example 1. For part A, draw in a line that appears to fit the scatter plot between the points 99, 258, and 105, 125. So real quick, on the graph, these are my x values, those are my y. Here's my x sub 1, y sub 1, x sub 2, y sub 2. Now it actually doesn't matter which one I chose to be the sub 1s or the sub 2s. So let's see, 99, 258. Right there. I'm going to draw a line between that one and 105, 275. Right there. I'm going to draw a line between those two, and I'm going to call that my line of best fit. What does that mean? Well, that's just saying that this line looks like it's sort of central to all of the data points. Okay, so if I look at that, that looks good. Let me draw a line that would not be quite as good of a line of best fit. For example, if I drew this line here in red, all the data points are above that line, so that one wouldn't fit that well. Or if I drew another line right here, that one's nice for a little bit, but then all the data points start to gather below it. So you want to find a line that's in between all of your data points. Now notice, we're doing this by hand, which is not going to give us the best kind of a line. But let's just take a look at what happens when we do it by hand. So we've drawn our line, and the next thing is to use the points 99, 258, and 105, 275 to create an equation for the line through the points. Okay, so as I mentioned before, if I want to create the equation of a line, it's easiest to start with the point-slope form. So let's go ahead and do that. I'll copy it down. And then what do I need to fill out this equation? Well, remember, I need a point and a slope. Do I have a point and do I have a slope? Let me write that down here. I need a point and a slope. Well, we have a point. Actually, we have 2 points. Look at that. Awesome. We have more than we need. So we have a point. Check. Do we have a slope? No, we're not given a slope. Darn. How do I find a slope? Well, let's see. What are my ways to find slope? I have rise over run. I can't really use that technique here because these dots are not perfectly on my line, like a normal line would. So rise over run doesn't work here. How about this one? Using an equation. Well, I'm trying to find an equation, so that's not going to help us at all. This one will work because I need 2 points to fill it out. And notice, I have 2 points. So let's use the second method for finding slope. So find slope. I'll write this out. So some books will have y sub 2 first, and some books will have y sub 1 first. It actually doesn't matter. As long as, let me write this out, as long as these sub 1s are above one another, and the sub 2s are above one another. So you should not ever write your equation like this, with the sub 1 and sub 2 above each other. So that would be wrong. You need the sub 1s over the sub 2s. Let me erase that. Okay. So let's color coordinate this so we see what's happening. Y sub 1 is 258. Then I'll do y sub 2 right there, x sub 2 right there, and lastly x sub 1. Okay, let's go ahead and plug these guys in. I always use parentheses because we're dealing with a minus. Let me actually make that parenthesis a little bit bigger because that's a 100 number. Okay, so 258, 275, x sub 1 was 99, x sub 2 is 105. Alright, so now we can go ahead and do these subtractions. And let's see, we will get, it looks like 17 over 6 when we simplify that out. Which, when we slap that into a calculator, we get 2.8333. So m equals, I'm going to draw my line down to indicate where m is. M equals 2.8333. So now we can fill in our equation. I have my slope right here. So 2.8333. And then I have my point. So I'm just going to go ahead and use those sub 1s. I have 258 and 999. So plugging x sub 1 with 999 and y sub 1 with 258. I can go ahead and substitute those in. So I have y minus 258 equals 2.8333 times x minus 99. Now, I didn't say it in this problem, but most of the time you want to rewrite the equation of your line in slope-intercept form. So let's go ahead and do that. Well, slope-intercept form, we solve for y by itself right there. So I'm going to do that. So I'll add the 258 to both sides. And then I have y equals 2.8333 times x minus 99 plus 258. Almost there. Let's go ahead and do the distribution. And I'll get y equals 2.8333 minus 280.4967 plus the 258. Combining these two like terms right here, I'll get y equals, oops, I forgot the x there, 2.8333x minus 22.4967. And there we have our slope-intercept form. So this is the equation of a line through the 2 points that we indicated. And notice my y-intercept is 22.4967, and my slope is 2.8333. All right. So if we wanted to predict something, for example, if I wanted to predict how far a golf ball will travel when it is hit at a certain speed, I would let x equal certain speed, let x equal the speed we wanted, and then I could calculate out, ooh, that was an ugly speed. I could calculate out how far the golf club will go by what I find for y. Okay, so now let's take a look at actually finding the least squares regression line. So if you notice in the example above, I picked two random points to decide what I think looks like the best sort of middle point between all of my data points. But I just did this by eye, and this is all based by my graph, and notice my graph is even scaled weird. This is by 1s, the y's are by 5s. How do I even know that that's the best line, the best fit line for my points? Well, this is where the least squares regression line comes in. So the question was the line we created in example 1 really the best fit line? And the answer is, we don't know. It was all done by eye. Before we jump into the least squares regression line, there's a word we need to know. And the difference between the observed and predicted values of y is the error, or the residual. Okay. So let's look at the definition for least squares regression. Or actually, this is the criterion for least squares regression. So the least squares regression line is a line that minimizes the sum of the squared errors, or residual. This line minimizes the sum of the squared vertical distance between the observed values of y and those predicted by the line y hat. We represent this as minimize the sum of residuals squared. So notice what this is saying, for example, with our line up here, is the vertical distance between the observed. So let's say that this, with our line here, this would be my predicted value for this one right here. Okay, so this distance is pretty small. But what we're saying is there could actually be a better line, which we use for the least squares regression line, let's say in green, which says that actually, oops, let me back this up, that actually this is the best line. And that would be the least distance between my predicted value, which is in the green, and my actual observed value of y. Okay, so that's our goal. We want to find the line that has the least distance between the observed and the predicted, observed and predicted, observed, predicted, and so on. So notice these are all the observed values, and the predicted values, which would fall, oops, on my blue line. We want to find the line that has the least distance between those. And that's where the least squares regression line comes in. So least squares regression line. The equation of the least squares regression line is given by the following. Y hat equals b sub 1 x plus b sub 0. So notice this looks a lot like slope-intercept form, which we just went over, where p sub 1 equals r times sy over s of x is the slope, and b sub 0 equals y bar minus b sub 1 times x bar is the y-intercept. And note, x bar is the sample mean, and s of x is the sample standard deviation of the explanatory variable x. And similarly, y bar is the sample mean, and s sub y is the sample standard deviation of the response variable y. Alright, so very similar, except this time we're bringing into account the standard deviations and the sample means of our variables. So example 2, finding the least squares regression line by hand. Okay, so we're given our x bar. So actually, we're given our arm, we're given our mean and standard deviation for x, and then we're given our mean and standard deviation for y. So awesome, we don't have to find those. Now we're told to find the least squares regression line. Okay, so we know that the equation for the line is y bar equals b sub 1 x plus b sub 0. To fill this out, as usual, we need our slope and our y-intercept. Well, how do we find those? Well, from our definition above, b sub 1 is r times s sub y divided by s sub x. So b1 equals r times s sub y divided by s sub x. So what are r? R is that value there. S sub y is that. And s sub x is, oh, I should use a different color. S sub x is that different enough? Let me find a different. There we go. S sub x is that value right there. Okay, so plugging those numbers in, we get negative 0.946 times 5.612486 divided by 2.44949. That all simplifies out to negative 2.1676. So that's my B1 value. So I write this equals B1, B1, and box my answer. Okay, so as usual, the way I show my work in the lecture notes is the way I'm looking for you to show your work in your exam. Okay, so if you ever have a question on how much work you need to show, just take a look at what I did for the problems in the lecture notes, and that's basically what I would expect you to show as well when doing equations by hand. Alright, now what do we need to find? We need to find b sub 0. So b sub 0, what's the equation for that? Well, that is y bar minus b sub 1 times x. So let's do that. Y bar minus b sub 1 times x bar. So that's my mean. Changing color. Y bar right there. And then let's pick another color. Oops. X. Oh, these aren't doing that well. Oh well, running out of colors here. I have a limited palette. And B1. And B1 is right here. So we're using what we found. So notice you need to find B1 first before you find B sub 0, because B sub 0 uses B sub 1 in the equation. Alright, so y bar is 10. We're subtracting from that B sub 1, which is right there, the negative 2.1676 times x bar, which is 4. Plugging that into our equation and calculating that out, we get 18.6704. That's a nasty 6. Equals, and I'm just going to go ahead and tack on the b sub 0 there. Alright. Okay, so we have found, finally, b sub 1 and b sub 0. So we have our b sub 1 and our b sub 0. Let's go ahead and plug them into our equation. So y hat equals b sub 1, which was negative 2.1676, times x, plus b sub 0, which is 18.6704. And there we go, we have found the least squares regression line, given the data. Alright, so note, refer to the book on page 193 for how to use the least squares regression line using technology. Okay, so make sure to use that for your homework, but always practice doing it by hand for the exam. Okay. Objective 2. Interpret the slope and y-intercept of the least squares regression line. Interpreting the slope for the least squares regression line has a minor twist compared to interpreting algebraic slopes. Alright, so for algebraic slopes, there's a way to interpret the slope. In statistical models, such as least squares regression lines, equations are probabilistic. What a word. Oh, I'm running out of too many words here. Let me just make sure I spelled that right. Probabilistic. Yep, probabilistic. That's a fun word for Scrabble. Alright, so this means that any predictions or interpretations made as a result of the model are based upon uncertainty. We do not want to imply that there is 100% certainty behind their interpretation. So that's the thing with statistics and the least squares regression line. This is a probabilistic model. We are uncertain. There's not 100% certainty that the line we draw will predict future results correctly. We could get close, but we're not 100% certain. So for example 3, if you used your least squares regression line and found out that the slope was 3.1661 yards per mile per hour, how could you interpret the slope in statistics? Okay, so what this is saying is that over the course of the data we collected, on average, we observed that the increase in the club speed of 1 miles per hour increased the distance by 3.1661 yards. Okay, so each time this club speed increased in 1 mile per hour, the yard we observed was increasing by, on average, 3.1661 yards. So how could we write this out? If club head speed increases by 1 mile per hour, the distance the golf ball travels increases by 3.1661 yards. And as usual, because we're not 100% certain, we would write on average. Okay, so we're not basing this on certainty. We're just saying it's probably what's been happening by what we've observed. So notice the big if and the fact that we say on average, slightly disclaiming some things. Another way we could write this is if club head speed increases by 1 mile per hour, hour, the expected distance of the golf ball will travel increases by 3.1661 yards. Okay, so once again, we put in some slight bits of doubt. The expected distance, okay, and if. So we cannot say with 100% certainty this will happen. We're just saying, by the data we've collected, looking at the way we think we can predict things, this possibly could be the next move. Once again, statistics is not a super fine, perfected art, you could say. Alright, so interpreting the Y-intercept. So, in an equation, for example, this value right here is our Y-intercept. So what does that number happen to mean for our problem? Well, real quick, in case maybe you've forgotten what a Y-intercept is, if we have our Cartesian coordinate plane, remember with y and x, and you have a line that passes around through it, the Y-intercept is the point where my line crosses the y-axis. Okay? And where is that point? Right here. That point is called the Y-intercept. And notice there's only one for this line. Another Y-intercept, let's say for example my line looked like this. Then I would have that one Y-intercept right down there. Okay, so that's what the Y-intercept is visually. But let's take a look at what we could use it for interpreting in terms of our problem. So for interpreting the Y-intercept, is 0 a reasonable value for the explanatory variable? These are questions we're going to ask ourselves. So let's think of different types of problems. If we're talking about the amount of money I have in my wallet, is 0 a reasonable amount of money to have in my wallet? The answer is yeah, that's totally fine. Let's see. If we're talking about the golfing problem we've been using recently for all of our data, does it make sense to have a swing speed of 0 miles per hour? No, that does not make sense to have a swing speed of 0 miles per hour. So, for the money one, 0 would make sense. But for the miles per hour of my golf club, that would not make sense. Now let's think of another one. Do any observations near x equals 0 exist in the dataset? So similarly to the y, we'd just be sort of looking at our x values and asking ourselves, could these numbers make sense? For example, for the club head speed, would it make sense to start looking at a club head speed of 1,000 miles per hour? That'd be really hard to get to 1,000 miles per hour with a human swinging a club. So it wouldn't make sense anymore to start looking for x values like that. Okay? So when you're interpreting variables, make sure to ask yourself if it makes sense to even be looking for values at that point. So let's take a look at example 4. Determine whether, given the following explanatory variable, it makes sense to interpret the y-intercept. So for a y-intercept, so we're looking at for 0, part 1. 0, reasonable. So does it make sense to have a swing speed of a golf club being 0? The answer would be no. So this would be no. How about temperature in degrees Fahrenheit? Does it make sense to have a 0 temperature degree in Fahrenheit? It would make sense to be observing that, so that's fine, yes. How about the lengths of the sides of a rectangle? Would 0 be a reasonable length? No, it doesn't make sense to have 0 length. That doesn't exist, so the answer would be no. How about D, number of eggs in a basket? Does it make sense to have 0 eggs in a basket? Yeah, that's possible, so the answer would be yes. Alright, now let's take a look at objective 3, compute the sum of squared residuals. Alright, example 5. Compare the sum of squared residuals for the lines from example 1, which we had was y hat equals 2.8333x minus 22.4967, and the least squares regression line y hat equals 3.1661x minus 55.7966. So this is the equation that we found by hand for the first example we did, and then this equation here is the actual least squares regression line for the data we had. So what we're going to do is compute the sum of the squared residuals for them, and then compare them. So we're going to use the tables to compute the sum of the residuals squared by using the predicted values of y and y bar for the equations. The data is provided by the table to the right. Okay. So let's take a look. I'll make a table for the line that we had from example 1, which remember we did by hand. So we weren't actually using the least squares regression line. And then we're going to compare this with the squared residuals of the actual least squares regression line, which you would use with technology or finding all of those datas by hand. Finding all of the mean for x, y by hand, as well as the standard deviations. Okay, so this one is the best fit we did in first example, and this one is the least squares regression. Okay, so let's set this up. Alright, so I went ahead and set this up. So we have our x data values, which are given right here, the club head speed. Then we're going to go ahead and use those, plug them into our equation to find the matching y hat value. Then we'll find the residual, which will be my y values, which were the observed, minus the predicted values, y hat. After that, we'll take the square of what we found in this column. So I'll go ahead and do the first one. That will be 2.8333 times 100, because we're inputting x value into our equation as 100, and subtracting 22.4967, and what do we get? we'll get 260.8. Now, with that, we're going to find the residual. Oops, wrong pen. The residual is going to be my observed value, which was actually, oops, wrong pen again, observed value, which was 257, and we'll subtract it from the predicted value, which is 260.8. So that'll be 257 minus 260.8, and we end up with negative 3.8. And then lastly, what we'll do is we'll square that difference. So that'll be negative 3.8 squared, which is 14.44. All right, so I'm going to go ahead and fill out this chart. Check back in with me in a second. Okay, so I went ahead and filled in some of the main parts. So let's write down the values we would find for each of these. All right, so for 102, this one right here, what do we get? We'll get 266.5. Plugging that in, calculating that out, we'll end up with negative 2.5, and then plugging that into there, we will end up with 6.25. Let's do that with the next one. Oops, that's supposed to be 102. So then plugging in 103, we'll come out with the value of 269.3. So 269.3, which is going to end up equaling 4.7. Square the 4.7, and we get 22.09. Okay, I'm going to go ahead and continue filling this out. Check back in with me in a second. Okay, and so the last step after filling in all this information, let's do the squaring for the last step. We'll get 5.29, 4.0, 4.84, 0.0, and 0.0. So, what we were looking for is the sum of our residuals squared, which means we're going to add up these values to find the sum of our residual squared, which will be, when I add them all up, I get 56.91. Now, I'm going to compare this with the least squares regression. So we're going to do the exact same thing, this huge chart by hand for the least squares regression. Let me go ahead and set this up. All right, so I went ahead and I set up the chart. So, clarifying, I wrote down our equation for y hat. So remember, this is the least squares regression line, which is supposed to end up with the least squares difference. So we're going to go ahead, fill in the x values, plug them into our equation to find the matching predicted y values. After that, we'll take the subtraction between our predicted y values and the actual observed ones, which are from our data chart above. And then with that answer that we find here, we'll go ahead and square them. Lastly, we'll take those answers and find the sum. So let's go ahead and I'll do the first one with you all. So we'll do the 100, plug that into our equation. And then calculating out the answer, we'll end up with 260.8. Plugging that in here, 260.8, that's going to end up equaling negative 3.8. Oops, let me change the color on that. I'm going to do red. We'll square that. The residual, remember it's the difference between the observed and predicted value. Squaring the observed, or the residual, we'll end up with the answer of 14.44, which looks very similar to what we had previously for the first value. So now let's go ahead and keep filling this out. Check back in with me in a second. Okay, so I went ahead and I did finding the predicted y values. So now let's go ahead and do the subtraction between the predicted y values and our observed y values of y. Calculating those out, what will we get? We'll get to negative 3.1, 3.7, 2.0, 0.4, 2.2, 0.4, and a negative 1.6. Then plug those in here and take the square of each of them. So remember, The numbers in red are what is considered our residual. It's the difference between the predicted and observed values. And the visualization of that, remember if you have a line going through your data points, let's say the lines in black are the actual observed values when you collected your data, and then all of the dots that would be on your line are the predicted values. So the residual is the difference between your observed value and your actual predicted value from your line. Okay, so that's what we're looking at. Okay, let's keep calculating this out. Um, 14.4, so 9.61, 13.69, 4.0, 0.16, 4.84, 0.16, and 2.56. All right, why are we doing this? Because we want to find the sum of the residuals squared, or sum of the squared residuals. So add up our values, and we'll end up with 49.46. So the sum of my squared residuals for the line that we did, which we thought was the best fit, that's the sum, 56.91. And then the actual least squares regression line, which was given to us, the sum of that, or the residuals, was 49.46. So what do we know? Well, the sum of the squared residuals for the least squares regression line is smaller. And this is true. This is what it means. Least squares regression line is going to give us the line that will have the smallest least squares residual. So any other line we create would have a number bigger than 49.46, which is true, because the line we created had a residual squared of 56.91. So let's write this out. A line other than the least squares regression will have a sum of residuals squared greater, running out of space here, greater than 49.46 for this problem here. All right, and that's why we like the least squares regression line. It finds the line that best fits our data points. Alrighty, that's it. Please email me if you have any questions.